This is the second part of the lecture about Ancova. This time we analyze a real life experiment. The setup is the same. We have a group of students. This time there is 60 of them that are supposed to study for the exam using the traditional method or the usual method. Again, the first variable is the dependent variable, the result of the exam, which, as we can see here, is measured on the scale probably from 0, but ending somewhere at 800. And there is the covariate, which measures the performance in class. Performance in class is measured on the scale from 0 to, I don't know, 70 something, maybe 100. And we can see what are the data. The dependent variable in the control group, the dependent variable in the experimental group, and the overall histogram of the dependent variable in the whole sample. As usual, we do our scatter plots. Since these are real-time data, real-life data, we do not see as strong linear dependence as before. Maybe our choice of a covariate is not that good. Maybe we should also take something else into account, because this is rather a cloud of points than a line of points, and the same for the control group. As before, I'm sorry, the experimental group is in red and the control group is in blue. When we superimpose those two pictures, we can see that there is no clear separation between experimental group and control group. Maybe experimental group is a little bit lower. So in this experiment, new method gives probably a little bit worse results than the traditional one. However, again, from the picture, it is not that visible. Then we check for interactions here. And as we expected in real life data, the picture is not that clear as before. The slopes are different, and the question whether they are much different or not should be probably answered while testing for interactions, as we did before when analyzing choice of independent variables for multiple regression models. If we find the interaction statistically significant, then we should abandon this analysis or use Ancova version for interacting variables. For the sake of the lecture, we will assume that the interaction is not significant, and then we can proceed to the analysis. So first of all, we start with ANOVA. The same calculations are as before. So what we see, we have differences in exam scores in groups. In control group, the score is higher than in experimental group. It means that in this experiment, the new learning method was rather worse. than the traditional one. However, again, the relation is not very strong. 17% of the variance of the dependent variable is explained by the relation with our experimental variable. And when we look at p-value, we are now, if we assume a significance level 0.001, then we will be just on the verge. On the not significant side, but just on the verge. If we use the same significance level as before, 0.005, then we would consider this difference significant. And we can proceed to analysis of covariance and see what happens. Again, the same calculations as before. We compare the two regression models, the reduced regression with only a covariate and the full regression with a covariate and experimental variable. So what we can see here, we see that the linear dependence between the covariate and experimental and the result variable, the dependent variable, is not very strong. Again, only 14% of the variance is explained by the relation with the individual skills of students, which is small. When we add learning method to the picture, we get better quality of prediction. 31% of the variance is explained by those two variables together. And we have a partial correlation coefficient between the dependent variable and the experimental one with the control over covariance. And it is higher than before, of course. I mean, higher than 17%. This is almost 20%. but still, it is not very strong. So this information about the studying method is not very valuable in multiple regression model here. However, when we calculate the p-value, we get the p-value pointing toward significance. So the difference between the new method and the old method here is significant. And since new method gives worse results in the final test, we should definitely abandon this method of learning and stick to the traditional one, at least according to this particular study. So this is the end of this part, and then we proceed to the situation when our experimental variable has more than two values.